Morning. Welcome to Krishna's classroom. We continue with our working on integration theory. In this talk, we look at the well-known theorem, namely the Lebesgue dominated convergence theorem. So before that, we consider what is called the additivity over the domains of integration. So we will first work on that. This deals with this integral over, suppose A and B are two measurable subsets of E and A intersection B is empty, then integral over A union B is equal to integral over A plus integral over. Now this is the result that we are going to first look at. So let us state this as a theorem. Let f be an integrable over E. Assume A and B are disjoint measurable subsets then what we have is this. Now this is quite easy to prove because first of all we observe that f chi A, just to take the characteristic function of A, then and multiply f by the characteristic function of A, then the resulting function is equal to f on A and outside it is 0. Okay, so we look at these two functions. Consider now you know that both chi A and chi B are measurable. F is measurable. Therefore, f chi A and f chi B are measurable. The reason is that why this measurability is because A and B are measurable subsets. Therefore, now further they are also integrable. what we have is that mod f and mod f and since f is integrable, integral over e mod f is finite. So because of the monotonicity, it's quite easy to show that this is so. And now we look at this f of f chi A union B, that is also a measurable and integrable function because A union B is a subset of E and A union B is measurable, and therefore chi A union B is measurable, and therefore f times chi A union B is measurable. And this, of course, is equal to, because of the integral over E, okay, this is equal to P on E, which implies integral this is equal to and of course it's clear that this is equal to integral of f over a and integral over a of f over. That is pretty clear. Because that implies write this is equal to, this is because one can prove that integral over c f equal to integral over e of where c is of. So that completes the proof of this result. Therefore, it adds up. This is the point. When A union B equal to, when A and B are disjoint, then the integral over A union B equal to integral over A plus integral over, and this is a useful result. or in fact, one has to do this a bit, you have to verify that this particular property. Now we are in a position to introduce what is called the Lebesgue dominated convergence theorem. So, we have already seen that the integration and limiting process cannot be interchanged in all circumstances, and we need some extra conditions to facilitate this, and we have already explored one of them, namely that the monotonicity of the functions. Okay, so we had as a result we had what is called the monotone convergence theorem. That is one of the results that we have already established. Now we are going to establish another result which in a way a generalization of what is called the bounded convergence theorem. Okay, so this in a way generalizes that. Okay, so let us work on this. So statement of the theorem. Let be a sequence of measurable functions on E. Suppose there is a function G which is integrable over E and Fn on E in the sense that mod Fn G for every if sequence Fn converges to F pointwise almost everywhere on E, F is integrable over E and now just recall the type of condition that we had in monotone convergence theorem, because we simply assumed that Fn is a monotone sequence. That is the assumption that we have made. And now in the bounded convergence theorem, we assume that it's uniformly bounded by some m. This was the assumption that we have made. So what we have is that if Fn converges to F pointwise almost everywhere on E, then F is integrable over E, and limit n tending to infinity of integral over E, Fn is equal to F. This is the conclusion. To the proof of this theorem. The proof of this theorem is not difficult. Okay. So we have first, we look at the significance of this almost everywhere. Now what we have is this mod Fn is less than or equal to G for every n, and Fn converges to F almost everywhere on E pointwise. Implies mod F less than or equal to mod F less than or equal to G almost everywhere on. Now in the argument we can drop this almost everywhere for the following. See, it's on a set of measure 0 where this property may fail. Therefore, what happens is that you incise that particular set of measure 0 from it, and that is the complement of that particular set in E, where all these conditions are satisfied without the the tag almost every. Okay, and then what you have is this. You have on two sets. Suppose A is the set on which this property is not valid. Okay, but we know that it's a set of measure 0. So you have E can be broken up as E intersection E slash A union A. Now this is a disjoint limit. Therefore, you see that integral over E of f is equal to integral over E slash A plus integral over A of f. For that matter, any function which is where this convergence does not take place. So what happens is that here you see that this part is 0 because A is a set of measure 0. Therefore, it is this, and this is where you see the function fn converges to f on E slash A, and then we can prove everything on that and get the result, and eventually add to it the set of measures 0A on which these things may not be valid, but as far as the integral is concerned, it is not going to contribute anything at all because of this property. Okay, therefore we can ignore that. So we shall make a remark about this. By integral comparison test, Fn and F that is now, without loss of generality, we shall assume, at least for the sake of the proof, because all our statements will be that is on a set of measure 0, it may not be valid, but we can simply ignore that as far as integration is concerned. We may assume that F and Fn are finite and what happens is that if at all, see, according to the conclusion that Fn and F are finite almost everywhere, which means on a set of measure 0 they fail to be finite, but it's on a set of measure 0, and the contribution from the set of measure 0 is going to be to the integral is going to be 0. So we can justify this. Excise the zero A on which they fail to be finite. So that on finite. Now Fn may not converge to F on these sets. But that of course does not matter at all. Okay? Right? So we can use this fact that integral over E this can be made use of. So now without loss of generality we assume that they are finite on the entire E, because E slash A we take as E. So our argument is over there. In any case, if it works on E slash E, then it works on E because it is a set of measure 0 that adds to E slash A to get. Okay. So let us work on that. Let G minus Fn or we will consider these two is G minus Fn and G minus F. Now G minus Fn are properly defined on E. And they are non-negative and measure. So we are now looking at the sequence. So what we have is that the sequence G minus Fn, now this happens for every n. The sequence G minus Fn converges to G minus F. Now we can apply by Pato's lemma. Integral over E G minus F is less than or equal to limit infimum of integral G minus F. And by linearity of integration, we then have the following. integral over E f G minus integral over E f less than or equal to lim inf which is equal to integral over G minus lim inf in soup because of the sign change. Yes, sir. Because of sign change, you get lim inf replaced by lim soup. Therefore, we get one inequality from it. And that implies lim soup is less than or equal to integral of. So that is one of the inequalities that we get. Same way, now consider the sequence G plus F. G plus Fn, this sequence then once again apply Pato's lemma. Then what do you get? This is what you get. G plus F is less than or equal to lim inf well, and then by linearity of integration we have So we use these two inequalities. That is lim sup of this we have see lim inf is generally less than or equal to lim sup. Okay. It follows that these two inequalities integral over that is and which is equal to limit fn. Which is equal to f, and this implies limit that means the interchange of limiting process and the integration is valid. Okay, so I think we'll go back to this example and have a look at it. So you remember take E to be equal to 0 infinity. Now you take chi, the collection chi n plus 1. That is chi of the characteristic function of the interval n to n plus 1. Okay. So you see that chi n on E, and therefore but integral therefore what do you get in this case? In this case we see that integral E f is not equal to integral over E Integral over limit because this is equal to 1 whereas this is equal to 0. So inequality holds. Now in this example you observe that there does not exist an integrable G such that so if the conditions of the theorem fails to hold. Okay. So you see that here the problem is that what is it dominated by? At all you search for a dominating function, then it is going to be 1 everywhere. That is not an integrable function. So there does not exist an integrable. Only the dominating function, a dominating function is chi e not integrable. So that way you see that the particular example we have looked at does not satisfy the required condition. And this is an example for both. I mean, even the monotone convergence theorem conditions are not satisfied. Okay, so either way, this is not true. Okay. Thank you very much. I stop here today and then we take up some generalization of these theorems for discussion in our next lecture and we continue with it further. Okay. Thank you very much.